Hi, welcome back. In this lecture we are going to look at shaders and GLSL more in details. This lecture I want to make three key points. First, we use GLSL to program the OpenGL shaders. Second, we need to provide input and output variables to shaders. Third, uniform variables are a convenient way to move data to GPU memory at runtime. As I mentioned in the Hello Triangle lecture, shaders are little programs, the rest on the GPU. These programs are run for each specific section of the graphics pipeline. In a basic sense, shaders are nothing more than programs transforming inputs to outputs. Shaders are also very isolated programs in that they are not allowed to communicate with each other. The only communication they have is via their inputs and outputs. In the previous lecture, we briefly touched the surface of shaders and how to properly use them. We'll now explain shaders and specifically the OpenGL shading language more in detail. Shaders are written in the C-like language, GLSL. GLSL is tailored for use with graphics and contains useful features, specifically targeted at vector and matrix manipulations. Shaders always begin with the version declaration, followed by a list of input and output variables, uniform and its main function. Each shader's entry point is at its main function, where we process any input variables and output the results in its output variables. Don't worry if you don't know what uniforms are. We'll get to those shortly. A shader typically has the structure in the code presented here in the slides. When we are talking specifically about vertex shader, each input variable is also known as vertex attribute. GLSL has, like any other programming language, data types for specifying what kind of variables we want to work with. GLSL has most of the default basic types we know from languages like C, int, float, double, uint, and bool. GLSL also features two containers types we using quite a lot through these lectures, namely vectors and matrices. We will discuss matrices in a later lecture. A vector in GLSL is a 1, 2, 3 or 4 component container for any of the basic type I just mentioned. They can take the following form presented on this slide, where n represents the number of components. Most of the time we will be using the basic vec_n, that is vec1, vec2, vec3 and vec4, since floats are sufficient for most of graphics application. We can use .x, .y, .z and .w to access their first, second, third and fourth component, more or less like CUDA. Shaders are little programs of their own, but they are part of a whole, and for that reason we want to have inputs and outputs on the individual shader, so that we can move stuff around. GLSL defines the in and out keywords specifically for that purpose. Each shader can specify inputs and outputs using in and out keywords, and wherever an output variable matches with an input variable of the next shader stage, they are passed along. The vertex shader should receive some form of input, otherwise it would be pretty ineffective. The vertex shader receives its input straight from the vertex data. To define how the vertex data is organized, we specify the input variables with location metadata, so we can configure the vertex attributes as we saw in the Hello Triangle lecture. The vertex shader requires an extra layout specification for its inputs, so we can link it with the vertex data. Fragment shader requires a vec4 color output variable, since the fragment shaders needs to generate a final output color. If you fail to specify an output color in your fragment shader, OpenGL will render your object black or white. To send data from one shader to the other one, you have to declare an output in the sending shader and a similar input in the receiving shader. When the types and the names are equal on both sides of the shader, OpenGL will link those variables together, and then it's possible to send data between shaders. And this will be done when linking a program object. Uniforms are another way to pass data from our application on the CPU to the shader on the GPU. But uniforms are slightly different compared to vertex attributes. First of all, uniforms are global. Global meaning that a uniform variable is unique per shader program object, can be accessed from any shader at any stage in the shader program. Second, whatever you set the uniform value to, uniforms will keep their values until they are either reset or updated. To declare a uniform in GLSL, we simply add the uniform keyword to a shader with the type and the name. From that point, we can use the newly created uniform in the shader. Let's see if this time we can set the color of the triangle using the uniform. In the code I want to implement now, I want to change the color of the triangle at runtime. For this reason, first I retrieve the running time in seconds via GLSL getTime. Then I vary the color in the range 0 to 1 by using the sign function and store the results in a green value. Then I query for the location of the hour called uniform using GLGetUniformLocation. I supply the shader program and the name of the uniform to the query function. If GLGetUniformLocation returns -1, it means that it cannot find the location. Lastly, I can set the uniform value using the GLUniform4f function. Because OpenGL is in its core is a C library, it does not have native support for type overloading. So wherever a function can be called with the different types of OpenGL, OpenGL defines new function for each type required. GLUniform is a perfect example of this. The function requires a specific postfix for the type of the uniform you want to set. A few possible postfixes are presented here on the slide. If we want the color to gradually change, we want to update the uniform every render loop iteration, so it changes per frame. Otherwise, the triangle would maintain a single solid color, if only set it once. So we calculate the green value and update the uniform at each render iteration. Uniforms are a useful tool for setting attributes that might change in render iteration, or for interchanging data between our application and our shaders. We can put everything together now in a code called test_uniform.cpp. I can show a little bit about it, compile it, and run it. We can look first at the source code, looking at uniform. So the major difference is here. So now in the source code stores as a string in the code. In the source code at fragment shader source, we have a uniform vec4, our color. And then here we set it up, the frag color, that is our output, as the uniform we provide. Here the major change, we get time value using GLSL we change at each frame the green value. We get the uniform location, and then we set the uniform value, that is a vec4, using this green value. We can compile it and we can test it now. Here we go, we have our triangle change color in time. It's quite hypnotic, so it's better I stop it. We're done with this lecture. In summary, I stress 3 points. First, we use GLSL to program the OpenGL shaders. Second, we need to provide input and output variables to shaders. Third, uniform variables are a convenient way to move data to the GPU memory at runtime. In the next part of this module, we are going to look at matrices, transformation, and cameras in OpenGL. Talk to you soon!